by the Department of Homeland Security for the Transition to Practice program. And as part of that, we delivered the source code, the documentation, et cetera, to Sandia National Lab. And they did a pretty thorough red teaming of it. They red teamed all the technologies that were selected for this program and created a comprehensive report of it. And I believe that report is available to folks. David and Nadia said, actually, so that report's available if you'd like to see that. They deployed Hyperion on their farm member repository, and to the best of my knowledge, I talked to see her, they were still using it there. So it's been vetted by them. It's been put through its paces at 2 other organizations as well. We both done that. I don't think those reports are publicly available, and they checked the academy, which means no. But it's been through some pretty significant testing. Like I said, we have our own malware catalog here that we routinely run it over, and at least one of our other partners has a pretty comprehensive malware repo, and they pretty routinely run it over that and to see what they can catch it and discover.
All right, thanks.
Sure. What else can I tell you?
No, nothing else. Thank you. That's good.
So there's one question that came up. Can you describe where this may be in use without going into details of who is actually using it? So I guess I could mention that there's a commercial company, R&K Hybrid Solutions, that has licensed this for commercial use, and they are, and I think they're repackaging it to have nice GUIs, et cetera, but we didn't tell that much about here. It's been used by a number of other government entities have requested it from us under the government use rights, and we delivered it to them. And a couple of them are still in pretty close contact with us. We know that they're using it. I can tell you that they're using it to screen new software, and in one case they're using it for its original purpose, which is to analyze malware. So they're using it pretty heavily. I don't think I can name them yet, unfortunately, but it's in use. I'd say there are 6, maybe 7 organizations where this has been delivered and is in use. And as far as licensing goes, we have licensed it to one company, but we're licensing it on a non-exclusive basis, so we intend to license so many more copies of this. Yeah, I think we'll be the first by a second company. I think I reported that to you. So one thing I didn't do today was show you a live demo of the system. I'd be happy to do that. It's very text-oriented, because it's a image that you run sort of behind the scenes to scan software. There is an interactive version of Hyperion called the eViewer. If you'd like to see it, we can arrange a time to actually do a live demo of the system for you, but that's not within the scope of the time I have available today. Okay, I don't believe there's any other questions, so thank you, Stacey, for giving your time on this and going over this. Dan, do you have any other questions?
No, thank you.
Okay, thank you. Hello, and welcome to Oak Ridge National Lab's Invention to Innovation webinar series. Today's presentation is on the Hyperion cybersecurity technology that will be presented by Dr. Stacey Crowell. My name is David Sims, and I'm Commercialization Manager here at the lab. If you have any interest in licensing this or other technologies from the lab, please feel free to call me at 865-241-3808, or you can find my full contact information on the web at ornl.gov and follow the Our People link near the top of the webpage. Before getting into Stacey's presentation, I'm going to take a couple of minutes to give you an overview of cybersecurity technologies and capabilities here at the lab. We have over 30 researchers in the Cyberspace Sciences and Information Intelligence Research Group who conduct research in cyber warfare, situational understanding, visual analytics, and information dominance. This research is done in order to defend the nation's critical infrastructures against cyber attacks, to understand threats, in order to provide real-time, actionable intelligence, to secure supply chains and continue operational capabilities, and to defeat both known and future adversaries. The group is divided into 2 research teams, the Cyber Warfare Research Team and the Situation Awareness and Visual Analytics Team. Our guest presenter today is the leader of the Cyber Warfare Research Team, which currently consists of 13 people, 6 of whom hold doctorate degrees. The team studies methods of both attack and defense in cyberspace, and also manages the lab's Center for Trustworthy Embedded Systems, which operates a cutting-edge laboratory conducting research on the security of vehicles, medical devices, as well as the rest of the Internet of Things. To support this research, the team also operates and maintains its own private test networks, computational clusters, and storage units. The current research efforts include learning-enhanced moving target defense, physics-based intrusion detection systems, improvements in Internet routing, or enhanced resilience, and static analysis of compiled software, an example of which will be presented in today's webinar. Dr. Crowell is the Chief Cyber Research Scientist here at Oak Ridge National Lab, and his work focuses on applying high-performance computing and computationally intensive methods to understand automated reverse engineering, semantic analysis, system composition, and software forensics. In addition to being leader of the Cyber Warfare Research Team, Stacey also serves as a program manager for the lab's Cybersecurity for Energy Delivery programs and holds a joint appointment in the Electrical Engineering and Computer Science Department at the University of Tennessee. Stacey has managed commercial software development projects and has consulted on the design, development, and testing of a wide range of applications. He also holds a PhD in computer science from the University of Tennessee. More information about our technologies available for licensing can be found on the web at ornl.gov by following the partnerships link, which is about midway down the webpage. And in the next day or so, we'll have this webinar posted on YouTube, as well as a link to it posted on our partnerships website. So now I'm going to turn the microphone over to Stacey, who will provide a 15 to 20 minute overview of Hyperion, and afterwards he'll be available for questions. If you want to ask questions, remember to unmute your microphone, or you can email me questions at simsdl@ornl.gov. That's simsdl@ornl.gov. Okay, Stacey. Great, thank you, David. And do feel free to interrupt me as I'm going through this and ask questions if you like. So I'm going to tell you a little bit about Hyperion, and I'll try to get my 2-hour presentation down to, what did you say, David? You said, 1 hour? Okay, well, maybe. Let's see, this will work. Let me see if I can change slides with it, and it looks like I can. Can you copy to the next slide, please? Slide changing is another technology we need to work on. All right, great. We conquered the slide advance. That's wonderful things that technology has in ourselves. So really, Hyperion is trying to get at this problem that software tends to be delivered to you as a black box. It comes to you in this nice compiled form, ready to execute, and that's all well and good, but it contains programmed with unknown behavior. It may contain some ill-conceived behavior, poorly implemented protocols, weakly implemented crypto, weak random number generators, stuff like that. And it may contain correct behavior that is correct to its specification, but still insecure. And we need a way to discover all of this before adversaries do. We do have someone to find all this for you, it's your adversary. But we would like to know about it preferably before they do, because then we can take steps to deal with it. Wow. There we go. What we need is a rigorous assessment of the true functionality of programs. We need to be able to take a piece of compiled software and say what it does. It's a hard problem, but it's made harder by a number of factors. One of them is compilers. Compilers will come along and add value. They will they can strip out secure behavior, pretty well documented, and they can introduce compiler bugs. They add their own little feature to it. So you have to work with compiled software in order to get things done. And you have to consider all the behavior. One of the things that will lead folks astray is the use of heuristics early on. It seems reasonable to conclude that incrementing a register is the same as adding one to it, but on the Pentium, they're not quite the same. So that little highlighted line there shows you that one will modify a flag called the carry flag, the other will not. And we think that's not a big deal. That is, in fact, something that you see in malware. People can take advantage of this to determine whether or not they are being sandboxed or they're being emulated to debug, because emulators will tend to get this wrong. The intuition of people reading the code, they'll tend to get this wrong as well. You see an increment followed by a check on the carry value and make an assumption, and that assumption is probably going to be wrong. So, let me tell you a little bit about our solution to this problem, which is Hyperion. It's a system for doing static analysis, meaning we don't execute the software. We do some small amount of symbolic execution when necessary, but for the most part, it's swallowing the ocean kind of static analysis. We do not compile software. We can apply this to reverse engineer software to discover behavior. We've done it to compute similarity as well. The technology is fairly mature. It's been proven to work, and we've delivered it to a number of organizations. If you're familiar with the technology readiness level, this has been rated TRL 8. And basically what it does is showing that little figure at the bottom. You give it the bytes of the compiled program. You can give it a specification for a piece of behavior you're looking for, and those we'll talk more about. They tend to be fairly easy to write and maintain, and it will tell you whether or not it's present, and in fact tell you something about it if you find it. So Hyperion began live back in 2004 at CERT up in Pittsburgh. We built the initial version of it, applied it to polymorphic and virtualized code. There are some articles in the CERT research reports about it. And then in 2009, the project and the entire team, in fact, moved to Oak Ridge, and we changed names because it's important to deal with branding. We changed names from FX to Hyperion, and there's been many different applications of it here. One of the things that I would say was the primary contribution to technology after it moved was turning it into a product, turning it into something that was reliable, so you could deliver it. It had well documented, the training for it, etc. All that was built out at Oak Ridge so that we could have a nice stable base for which to continue to search. So here are the basics of how Hyperion works. We take compiled software, we perform disassembly, we handle anti-disassembly, which we'll talk a little bit about. We then do structured discovery, so we turn the disassembled program into a structured program. We do external call discovery, so if your program has no import table or the calls are obfuscated in various ways, we use information we discovered earlier in the process to reconstruct that and discover what the external calls actually are, what the arguments are, and then we do behavior discovery, which is where we actually use these patterns of behavior to recognize and document what it does. Right now, we have two platforms Hyperion can target. It targets 32-bit Intel, and it targets the MSP, the PCI MSP 430 embedded processor, just because those are the platforms that customers have access to deal with. So you're dealing with anti-disassembly, and if you're not familiar with it, there's a little example down on the slide here. If you look at the example on the bottom right, the first 4 bytes are move instructions. Those are followed by an XOR instruction that's exclusive OR the with itself. So the way of doing that is always 0. So that jump 0 takes you back. So you count backwards E, B, C, D, A, 9, and that takes you back to that jump 5 instruction, which you see was part of the original move instruction, but now it's being reinterpreted. You jump forward 5, and now you're into the real code. A straight line disassembly, so if you just point disassembler at this, you'll see the move, the XOR, the jump on is 7, but then you'll see a call instruction after that, and you'll be off and you'll not see the real code. So we have to deal with crazy disassembly, anti-disassembly techniques, funny things like that. The way that Hyperion deals with this is it allows, it does basically threaded disassembly. It allows a single address to appear multiple times in the final program, and the way we do that is sort of outlined on the slide here. We identify the entry point, we find main, we begin adding addresses to the stack and exploring the program, and that's almost true. And the reason it's almost true is because we have to do a little bit of everything to make any of this work. So it's a very iterative process. For example, we find main using a variety of methods, one of which is we look at the complexity of the structured islands we discovered. We typically find that main is the most complex of the structured islands encountered after the entry, and that works very well for us. So there are a number of ways that we can go about doing this, and they all require that you do quite a bit of work. But the end result is a a static disassembly even when you have the reinterpretation of some address. We then do structuring, we turn things into sequences and spin out those while loops, and we do extraction of it. So the sequences, it's function composition. Everything else is, it's a very simple function composition. For loops, it's a little harder. There are a number of techniques we can use. We can do loop slicing. There's some work that we've done on using relations. We find that loop unrolling, which I didn't something have with slide, we find that loop unrolling works quite well. We can often unroll the loop and discover what it's doing pretty readily. If that doesn't work, you can fall back on slicing other techniques. But what we get out of this is what we call a program function. So given a barrage of instructions, we boil that down to its net effect. So what you see there